Look out into deep space, and you will find massive, reddish-brown clouds of dust forming around supernovas and carbon-rich stars. Observations show that these dense, heavy shells of cosmic dust are materializing in as little as 10 years, producing individual grains up to 1,000 micrometers across. According to our baseline models of physical assembly, that timeline is impossible. The traditional theory relies on Brownian motion and accretion, meaning particles randomly bump into each other and stick. By that logic, a dust cloud of this magnitude should take up to 1 billion years to grow. When you run the math on those random, multi-directional collisions, the growth rate stalls out. There simply is not enough focused interaction in a vacuum to build such large structures on the 10-year timelines we are actually observing. If the equations fail to explain how the universe's oldest structures assemble themselves, our baseline understanding of how physical matter organizes is missing a critical variable. We face a similar mathematical disconnect in civil engineering, specifically when calculating the physics of massive concrete building foundations. For decades, engineers have relied on the standard elastic theory to calculate exactly how the ground will settle under the immense weight of these concrete slabs. The flaw in this elastic theory is that it assumes the structural pressure dissipates infinitely downward in all 3 dimensions. Because of this assumption, engineers consistently overestimate the depth of the active pressure zone, resulting in highly inaccurate settling measurements in the field. To engineer the heavy megastructures of the future, we have to discard idealized models and find the actual physical mechanics that govern how matter behaves under pressure. The solution to rapid assembly in a vacuum comes from physicist V.N. Tsytovich, who proposed a highly efficient mechanism for dust formation within charged plasmas. First, look at the baseline physical state. A dust particle floating in a plasma environment is constantly and violently bombarded by highly energized ions and neutral particles from every possible direction. When 2 of these dust particles drift close to one another, they block each other from that surrounding storm. They cast a physical shield, creating a low-pressure zone directly between them. Because their outward-facing sides are still taking the full violent force of the plasma bombardment, this shielding creates a massive pressure differential that literally forces the 2 particles to slam together. This creates a gravitation-like instability. It drives rapid agglomeration, entirely bypassing the agonizingly slow billion-year accretion model. Recognizing this invisible shadow force identifies matter formation as a process of active, pressure-driven assembly. This exact concept of pressure boundaries applies to the dirt under our feet. Researchers like N.A. Tsytovich studied how soil reacts under foundation slabs, occupying massive surface areas, specifically those stretching over 14 meters wide. Under slabs of this massive scale, the compacting pressure cannot dissipate infinitely outward. It becomes physically trapped, acting as a one-dimensional compression seal pushing straight down. This chart plots the maximum compressive stresses beneath a foundation. The curves labeled 1, 2, and 3 track how that vertical stress distributes through bounded layers of soil of varying thicknesses. Follow curve 1 downward. As the compacting pressure gets closer to an unyielding, incompressible layer of rock, the vertical stress stops dissipating and distributes far more evenly across the boundary. This diagram illustrates that exact one-dimensional compaction problem. The evenly spaced horizontal lines show how pressure distributes predictably when a massive structure sits on a thin layer of highly compressible soil. Proving that a new pressure boundary dictates the physics of a structure requires extreme rigor. We see the exact same demand for data-driven validation in theoretical physics, such as the intense investigation into Tsytovich's proposed radiative corrections for high-energy ionization loss. This document details the results of that investigation. The concluding text states clearly that the field data provided confirmation of the older Sternheimer density correction, and the newer Tsytovich theory was not observed at those high energies. Whether we are validating a new mechanical shadow force or confirming an older particle density model, true invention demands that we let raw data, and not assumptions, write the engineering roles. How do we extract these physics, the shadow forces, and one-dimensional compression, and use them to invent new technologies? If we artificially replicate the shadow force inside industrial plasma baths, we could force agglomerate novel, ultra-dense materials at speeds that are currently impossible to achieve. Applying the math of one-dimensional compression seals to our civil engineering gives us the exact physical justification needed to safely build architectural megastructures that older theories deemed impossible. Mastering these mechanics of pressure, shielding, and compaction provides the physical blueprints to construct buildings at scales that exceed our current engineering limits. If you enjoyed this breakdown, please like and subscribe to the channel, and a special thank you to the sponsor of this video, Synestex Systems LLC, and founder Shane Persinger.